All right, so in the last video we did one where we were launching something horizontally. Now we're going to be launching something at an angle. So if you haven't seen the last one where it's a horizontal launch, that's an angle of 0, I recommend you go back and watch that one before you attempt one that is launched at an angle, because number 3 here is going to use elements of the first two here, but now we're not going to have an initial y velocity of 0. So this one right here is talking about a diver jumping up off of a pier at an angle of 25 degrees with an initial velocity of 3.2 meters per second. They want to know how far from the pier will the diver hit the water. And you can assume that the water is the same level as the pier. So what I want you to do with this is to first draw a picture that kind of helps you see what's going on here. Then I want you to draw a triangle representing this 25-degree angle and a hypotenuse of 3.2 meters per second. Then I want you to list out an X and a Y column there for what is given and what is unknown. So I started this here. This is like the beginning of my triangle, 3.2 meters per second at a 25-degree angle. And then I have an X and a Y column, but I haven't finished filling out what's given and what's unknown. I haven't drawn my picture yet. So I want you to pause the video right now, try that out, and I will fill some of this out while you do that. All right, so there's your picture of what's going on, same level to same level. Here's kind of like a zoomed in version of what's going on with his velocity. We're going to let the x velocity be this way. That is the initial velocity in the x direction. And then upwards, we're going to call this the initial velocity in the y direction. So we need to solve for both the purple and the green here, and we're going to use trigonometry to solve that out. Our hypotenuse is 3.2, and our angle is 25 degrees. So if you go back to our trigonometry class, we've got that sine, cosine, and tangent. And we have opposite hypotenuse, adjacent hypotenuse, and opposite over adjacent, which I call Oscar had a heap of apples. Some of you may know it as SOHCAHTOA. In fact, most of you probably do, and you can use it at whatever works for you to do this trig. But this green side right here is the opposite of the angle that I'm talking about. That is OPP, and this is the hypotenuse. So if I want to know the opposite side, and I know the hypotenuse, the only trig function dealing with opposite and hypotenuse is the sine function. So I'm going to say the sine of my angle equals the opposite side divided by the hypotenuse 3.2. Multiply both sides by 3.2. And that will tell me my velocity in the y direction. So we've got 3.2 times the sine of 25. Make sure your calculator's in degree mode while you do this. That gives me 1.35. That is my initial velocity in the y direction, 1.35 meters per second. Let's do the same thing for x. So if you want to try that out, figure out your trig function and then solve for Vix, the initial velocity in the x direction. You can pause the video. All right, I'm assuming you paused it. Let's see if you got it right. You're going to have cosine this time because we're dealing with adjacent over hypotenuse. So the cosine of our angle is going to equal Vix over 3.2. Multiply both sides by 3.2. And that equals your initial velocity in the x direction. So 3.2 times the cosine of 25 gives me 2.9. So 2.9 is going to put in for the initial velocity in the x direction, and that, of course, is in meters per second. Now, that is the main difference between horizontal launched objects and anything launched at an angle. You have to do this step first. You have to break it up into an x and a y direction. After that, the rest of it is fairly close to being the same with a few exceptions. So we still have a velocity in the x direction that's going to remain constant. It's not going to change because there are no forces pushing it or pulling it left or right. So that tells me the acceleration in the x direction is 0 meters per second squared. It also tells me my final velocity in the x direction is the same as the initial, 2.9 meters per second. And it also says that the average velocity, if I want to know it, is also 2.9 meters per second. What's unknown here in the x direction is delta t and delta x. Delta x is what the question is asking for. How far is this diver going to land in the water? Delta t, just like in horizontally launched things, is the one thing that connects vertical motion in the y direction and horizontal motion in the x direction. That delta t has to be the same for both directions. Everything else can be different. The acceleration in the y direction, I'm going to let down be negative, and this is going to be 10 meters per second squared then, since down is negative. The final velocity in the y direction, a lot of times I can't tell this right off the bat, but in this case, since it's going same level to same level, the initial y velocity is going to slow down to 0 up here at the top, and then right before it hits same level going down, it's going to be the exact same magnitude of velocity, but the opposite direction. So since this was a positive 1.35, it's going to be negative 1.35 meters per second right here. So I can use that. Also, because this is same level to same level, my change in height, or my delta y, will also be 0 meters. So I got a lot of information there I can use. I still don't know what delta t is. That's unknown. So I figure out delta t here, I can put it in right there, and then solve for delta x. I want you to pause the video, see if you can figure out what equation to use and solve for delta t. All right, I've taken it that you've taken a moment and tried to figure this out. If we, I think the easiest way to use this is to say VVAT, or final velocity equals initial velocity plus acceleration times delta t. So our final velocity is negative 1.35. Our initial is positive 1.35. The acceleration is negative 10. And then we've got time written right there. I'm right with a marker, so it's hard to see, but if you're listening, then you can hear everything. So if I subtract 1.35 from both sides, I got negative 1.35 minus 1.35. Remember, this is negative because the final velocity is going in the downward direction. I get negative 2.7. That equals negative 10 times my time. Divide both sides by negative 10, and I get a positive 0.27. That's how long it's in the air. So vertically and horizontally, 0.27 seconds. Now, a lot of times, this is same level to same level, so it made it super easy for me because I could figure out the final velocity in the y direction because it's the same speed, but opposite direction as the initial y velocity. If you don't have that final velocity, because a lot of times it might be like he's diving off of a diving board or something like that, so it's a different level, then you might want to use something like delta y equals initial times, here I'll write it out, delta y equals initial velocity in the y direction times time plus 1/2 times gt squared, where g is the acceleration due to gravity. So that's a good one. Notice we don't have final velocity in that equation, so you could still figure out time here. It's just going to be a little more complicated because you're going to have to use like the quadratic formula to solve it. But this one, same level, made it nice and easy for me. And now I can say, hey, in the x direction, that's what I'm going to be working on next. If I want to know how far I go in the x direction, and I know how fast I'm going, 2.9, and I know how long I'm going that fast, 0.27, then I can multiply these two and figure out how fast I go. So for instance, if I'm going 10 miles per hour for 3 hours, think about that, 10 miles per hour for 3 hours, I'm going 30 miles. You just multiply my rate times my time. This is 2.9 meters per second times 0.27 seconds. So when I multiply that out, I should get my answer here. 2.9 times 0.27 equals 0.783 meters. 0.783 meters. He's not going to go that far. So at that angle, I mean, you think about what a meter is. It's a little bit about a yardstick. So you're looking at around 2 feet off of there. So not much of a dive there, but that is our answer, 0.783 meters. Thanks for watching. I hope you had a good time doing this. And if you have any questions, let me know.